that might produce a different knot, but these seem to produce the same knot. Okay. So I guess the comment I'll make here is the Reidemeister moves, and I'll let you think about it. There's no use in belaboring the point, because probably somebody think I'm belaboring the point a lot here, but the Reidemeister moves keep the knot itself, maybe that's not the best. The Reidemeister moves keep the knot itself the same. Another way to say it, the Reidemeister moves don't produce a different knot. Maybe that's a better way to say it. The Reidemeister moves don't produce a picture, a projection, I guess, of a different knot. So they're kind of good moves in that regard. One kind of move you might make, which is an interesting move, is given a, so let's call this a little side comment. When you see a part of the picture that looks like that, you might be tempted, I'll just change the crossing. So here's, it's over, here, this is under. Let's just flip it, so this is like over and this is under, and the rest of the picture remains the same. You might be like, I like that. It's called a crossing change. You might say, like, I like that, just changing the crossings willy-nilly. But it turns out, if you do that, you can always get a picture of the unknot. So that's one of the exercises in the sections you're reading. You can always take any projection of any knot, like any one of the ones in the book, and change the crossings in different kinds of ways, and you get a picture of the unknot. So it's not a very good kind of modification in terms of sort of trying to understand what kind of pictures you get. Well, so here's Reidemeister's theorem. The Reidemeister's theorem is sort of, you know, the other way, which is it seems pretty obvious that if I get two pictures that are related by Reidemeister moves, they represent the same knot. But it's not so obvious that if I have two projections, basically two descriptions of the same knot, that I can relate them by Reidemeister moves. Because two pictures of this same knot are obtained by projecting them, right? You take some knot, you move it around in some crazy way, you can stretch it, you can shrink it, blah, blah, and then you project it, you get another picture. It's not so obvious that whole complicated thing you did is describable by a sequence of these simple moves, like the type 3 move, type 2 move, some sequence. It might be kind of long, but it doesn't seem obvious that there is any sequence, right? That's not so obvious upon first or even second thought, I think. But Reidemeister's theorem says, suppose D1 and D2 are two knot projections, then D1 and D2 represent the same knot, and I guess here's a term I'll explain if you've never seen it, is if and only if there's a sequence of Reidemeister moves, there's a sequence of Reidemeister moves I guess, I don't know if people can really see down there, so let's talk here. Sequence of Reidemeister moves taking D1 to D2. That's the end of the theorem. So, if and only if, what does that mean? If and only if basically means, let's look at the statements on either side of this phrase. D1 and D2 represent the same knot, and that there is a sequence of Reidemeister moves taking D1 and D2. If and only if means one statement's correct if and only if the other, one statement's true if the other one's true, and if the second one is true, then the first one is true. So they're true or false at the same time. Like, so if, in other words, if D1 and D2 do represent the same knot, then there's going to be a sequence of itemized removes connecting them. So that's not very obvious, but the other direction is a little bit obvious, which is if there is a sequence of itemized removes taking D1 and D2, then D1 and D2 do represent the same knot. So it's an equivalence of these sort of two mathematical statements. So that's what if and only if means. So sometimes people say if and only if is like a equivalence of these two things. Okay, so any questions? Winnie?
Is that the same as IFF?
IFF? Yeah, kind of a funny question. Because IFF is even more kind of esoteric than, but maybe if your natural language was in English. Maybe Jesse?
The three type of moves you said that you can do. Are they the only types of moves you can do?
To do what?
I mean, well, what are you doing with that?
Well, you can do many moves to a projection of a knot.
So what are those
Think of whatever you want to do. You can do many things. I can erase the picture and replace it by whatever in any piece. Like I could replace a crossing like this with a crossing like that. I can do many things. But the point is, these three moves still give you the same knot. It's a different looking picture, but it gives you the same knot. And then I can do these moves all like in different order, like repeatedly. I can do type 1 like a bunch of times, type 2, then type 3, mix it up with another type of type 1, etc. I can do it a bunch of times. And I know at the end of it I get the same knot. But it might be a much more complicated looking picture. For example, I drew a picture of, actually there's some pictures in the book of the unknot which look very complicated. And I guess the point of Reidemeister's theorem is the other way is true too. If I give you a picture of, say, a knot like the unknot, and I give you another picture of the unknot, they're not obviously related by these Reidemeister moves, but the theorem says they are, in some way. They are connected. So what it means is, we know two pictures represent the same knot if you can deform the knot corresponding to one picture to the other knot corresponding to the other picture. We know if the knots are the same, then there's this deformation, but that's something that's happening in three-dimensional space, and it's like very complicated. I could go like this and go, woo, and then look at the resulting picture when I project. Well, that thing I just did is I can duplicate the effect of the beginning and the end pictures by a sequence of Reidemeister moves. So that's not so obvious, right? If I did it faster, it'd be even less obvious. Let's say we start with a projection that, we project it and we get this nice picture with over and under crossings, and I go dip it even faster, it's less obvious. But the result is obtainable by Reidemeister moves. So the theorem basically reduces knot theory to just understanding when two pictures are connected by Reidemeister moves. Now it's a little bit harder than that because, say you try to connect two pictures by Reidemeister moves and you fail. Right? Does that mean there are different knots? If you have two pictures, do they represent different knots if you failed after, say, 2 hours of trying to find Reidemeister moves? Yeah. 2 hours? 3 hours? What do you suppose the book says? Maybe the book says 4.5 hours? No, you just never know. I mean, it's just like anything else. There's a sequence, but how can you find a sequence of Reidemeister moves? There might be a very complicated path, sort of from one picture to the other, and you don't know. So just because we did this, turns out we have still some difficult problems to answer. All right?
What if there's a really complicated knot and there's one knot that cancels the rest of the knots out?
No, that's a different topic that we're gonna get to. Do you have a question about this stuff, the Reidemeister moves? Yeah. So not good. You can ask me after class. Okay. So so let's talk about tricoloring now. And I guess we'll just cover that the next time, unfortunately. But next time I'll go over this proof of tricoloring.